In the previous video, we discussed solubility and the factors which determine it. Today, we're going to talk about colligative properties. Before we get into that, I did want to draw attention to the new format for these videos. Instead of using a sort of written format, we're going to try and see if this typographic style is any better. It's easier to work with, it's far neater, and with any luck, it should work better than what we've been using thus far. We might have guessed by now that the physical properties of a solution are going to differ from the physical properties of the constituent solvent and solutes. Colligative properties are those physical properties which are dependent on the amount or concentration of the solute or solutes in a solution. The crucial point here is that colligative properties are not dependent on the chemical identity of the solute or solutes. In other words, it doesn't matter what chemical or chemicals are dissolved in the solution when it comes to the colligative properties of said solution. All that matters is how much of the solute is present. There are four main colligative properties we need to discuss. The first two, vapor pressure and osmotic pressure, these two, we'll talk about in our next video. The properties we'll be focusing on today are the boiling point and the freezing point of solutions. Now, before we can talk about how adding a solute changes the boiling point and the freezing point of a solution, we have to understand a concept called molality. Molality is related to molarity in that it expresses how much of a certain solute is present in a solution. The difference is that molality has units of moles per kilogram instead of moles per liter. Now, this is something we have to note. The units of molality are moles of solute per kilogram of solvent. Kilogram of solvent, not kilogram of solution. Why is this important? The reason this is important is because adding solute to a solvent increases the volume of the resulting solution as measured in liters. It does not, however, affect the mass of the solvent, which stays constant. Remember, molarity, which we discussed previously, is measured with units of moles of solute per liter of solution. Of solution, not solvent. Because colligative properties depend only on the amount of solute present, we need to use a parameter that does not depend on the volume of solution, since the volume of solution changes as we add more solute. The bottom line is that a higher molality results in a greater change to a solution's boiling point and freezing point. There is a direct relationship between molality and these two colligative properties. Let's take a deeper look at boiling point. The boiling point of a substance is, as we most likely know, the temperature at which a liquid substance becomes a gas. The premier example of this is steam. When water reaches a certain temperature, it stops being a liquid and becomes a gas. It goes from being one state of matter to another. Now, the boiling point of a solution is always higher than the boiling point of the constituent solvent. I repeat, the boiling point of a solution is always higher than the boiling point of the constituent solvent. To put it another way, adding a solute to a solvent always raises the boiling point of the solvent. The raising of boiling point via the addition of solute is called boiling point elevation. The boiling point is being elevated. It becomes higher than it was before. However, and this is just a clarification, we should know that boiling point also increases with pressure. For this reason, the International Union of Pure and Applied Chemistry has defined the standard boiling point of a substance as its boiling point at a pressure of 1 bar. The bar is a unit used to measure pressure, and 1 bar of pressure is very slightly less than the pressure exerted by the atmosphere at sea level. So, if a person is standing in a location that is at sea level, the force the air above their head is pushing down on them is the atmospheric pressure, and this is almost equal to 1 bar. When we talk about water, for instance, we most often cite 100 degrees Celsius or 212 degrees Fahrenheit as the boiling point of water. But if we traveled up a tall mountain, there would be less air above our heads, so the atmospheric pressure would be less than that at sea level. Accordingly, the boiling point of water on top of Mount Everest is lower than its boiling point at sea level. There is a direct relationship between pressure and boiling point. This is why the IUPAC decides to standardize things by setting a standard boiling point. Our second colligative property is freezing point. The freezing point of a substance is the temperature at which it goes from being a liquid to being a solid. Our example for this is ice. Ice is just water at or below its freezing point. In this way, we can see freezing point as moving in the opposite direction as boiling point. When we want to boil something, we want a higher temperature to make it go from a liquid to a gas. When we want to freeze something, by contrast, we want a lower temperature to make it go from a liquid to a solid. In this same vein, the addition of a solute always lowers the freezing point of the resultant solution. The solution will always have a lower freezing point than the constituent solvent. Lowering the freezing point by adding solute is termed freezing point depression. The freezing point is becoming depressed. It's being lowered. Like boiling point, freezing point generally increases with pressure. Water is one of those rare exceptions. The freezing point of water actually drops with increased pressure. To help standardize matters, the IUPAC sets the standard freezing point of all substances as their freezing point at a pressure of 1 bar. Before we get into the quantification of boiling point elevation and freezing point depression, let's talk about some practical applications of these two processes. We can accomplish this by returning to our old friend, sodium chloride. Sodium chloride functions as a solute in many cases, and in terms of boiling point elevation, we can add salt to water when cooking rice or pasta in order to increase water's boiling point. This way, when we add the rice or pasta or whatever it is we're making, the water will be hotter than if we didn't add any salt. Higher temperatures are usually desirable in cooking, so this is a useful example of boiling point elevation in action. Salt can also do the opposite. Whenever it snows, some cities will place salt on the streets. This lowers the freezing point of water, which is what snow is made of at the end of the day. When the freezing point is lowered in this manner, the outside temperature must decrease much more for ice to begin forming on the roads. If the natural temperatures don't fall that much, then less ice will form, and driving conditions will be far less dangerous because of it. This is where we arrive at the math behind it all. We begin with boiling point elevation, which I'm going to call BPE from now on. BPE is expressed as the variable delta TB, which just stands for the change in boiling temperature. This will always be a positive number. We can express the equation as the boiling point of the solution minus the boiling point of the pure solvent. Or, alternatively, we can express it as K sub B multiplied by M, where M is the molality and K sub B is a constant called the boiling point elevation constant. Then we have freezing point depression, or FPD. FPD is delta TF, which again stands for the change in freezing temperature. This will always be a negative number. Delta TF is equal to either the freezing point of the solution minus the freezing point of the pure solvent, or to the molality multiplied by another similar constant, K sub F, which stands for the freezing point depression constant. These two constants are what we want to focus on for the moment. They both have units of degrees Celsius times kilograms all over moles, as shown in the brackets here. These constants will vary for different substances, and it's not actually possible to calculate them all by ourselves. They're usually determined by doing experiments with solutions at different molalities and finding out the change in boiling point and freezing point. From that data, we can calculate the constants, but in a classroom setting, we'll most often be given the constants in the problem we're trying to solve. And remember, these constants, k sub b and k sub f, these constants are properties of the solvent. Properties of the solvent, not of the dissolved solute or of the resulting solution. The constants are different for each solvent. Our final notes on these two constants is that the BPE constant is technically referred to as the abelioscopic constant, and the FPD constant is the cryoscopic constant. That's enough information for now. Let's try an example problem. There are two primary types of problems relating to BPE and FPD. The first type encompasses problems like this. Example 1 says, determine the boiling point of a 5% solution by weight of dextrose in water. Assume the molar mass of dextrose is 180.1 grams per mole, and a BPE constant of water is 0.512. Dextrose, for anyone who's curious, is a type of sugar that can be administered for patients suffering from dehydration or low blood sugar levels. We're also introducing the concept by weight, which just means that in a 1 kilogram amount of a dextrose in water solution, 5% of that solution will be dextrose. Since 1 kilogram equals 1,000 grams, 5% of that will be equal to 50 grams of dextrose dissolved in 950 grams of water. Our current job, however, is to determine the boiling point of a solution. The first step is to determine the molality of the solution itself. Molality, remember, is the moles of solute per kilogram of solvent. If we assume that we're dealing with 50 grams of dextrose, we divide that by the molar mass, one 180.1 grams per mole, and obtain 0.278 moles of dextrose. In 950 grams of water. 950 grams of water is equal to 0.95 kilograms. And so we divide 0.278 moles by 0.95 to get the molality, 0.293 moles per kilogram. Our boiling point elevation is then (0.293) times the BPE constant, (0.512), and this is equal to 0.15 degrees Celsius. But we're not done quite yet. This is the change in the boiling point, not the boiling point of the solution itself. We know the standard boiling point of water is 100 degrees Celsius, and if this solution's boiling point is elevated by 0.15 degrees Celsius, then the answer must be 100 degrees plus 0.15 degrees, which is simply 100.15 degrees Celsius. So only a minor adjustment in boiling point. Example 2. Approximately 20 grams of unknown solute are added to 100 grams of formic acid. The freezing point decreased by 4 degrees Celsius. Calculate the molar mass of the unknown solute if the freezing point depression constant of formic acid is assumed to be negative 2.8. In this case, we are trying to determine the molar mass of an unknown solute by looking at the depression in a solution's freezing point. Molar mass is one of those parameters that gives us a clue as to what an unknown substance might be, so this is important to know how to do. Formic acid, by the way, is a type of acid found in ants and stinging nettle plants. Some ant species in the Forminiaceae family can actually inject formic acid into a person's skin, and this causes quite an unpleasant rash. We've already given the FPD constant and the FPD itself. All we need is the molality. Let's set up our equation. FPD equals K sub F multiplied by M for molality. We divide -4 degrees by -2.8 to get 1.429 moles of solute per kilogram of formic acid. We can then get rid of the kilogram unit by multiplying this by 100 grams, or 0.1 kilograms of formic acid, getting 0.1429 moles of solute. The problem says that 20 grams of unknown solute were added, so we simply divide 20 grams by 0.1429 to obtain 139.96 grams per mole as our molar mass of the unknown solute. From here, we could, if we wanted to, check a handbook of chemicals to find out which substances have a molar mass equal to or close to 139.96 grams per mole, and thereby determine the identity of our mysterious solute. In our next video, Unit 4, Video 5, we will introduce the very important concept called equilibrium. Thank you for watching.